Hi everyone, Unit 4 Atomic Physics, Section 3 Subatomic Models. This is Chapter 17 in your textbook. So there's a bunch of curriculum outcomes I want you guys to read on your own. Okay, and then there's the checklist for things for Section 3. So this is 4 parts, and you'll notice by the notes package it's very short. Okay, so 4 parts, and then you have a curriculum review, okay, atomic physics quiz, okay, and then of course your atomic physics unit exam. Okay, the formative assessment, so that's the atomic physics quiz and the atomic physics unit exam, will cover material from Section 1, Section 2, and this section, Section 3, and it will all happen at the end of this section. Okay, so it should be good for you guys to know, and we'll just scroll down for the little picture of the quarks that you're going to learn about here right away. Alright, so part 1. Before we start this, guys, I just want to throw this out there. This unit is highly theoretical. Okay, the videos will be short. The questions will be, again, highly theoretical. There's lots to think about. There's not a lot of questions on this on your diploma exam, and the ones that are again some theory, a little bit of magnetic force, centripetal force, that kind of stuff. Some fairly simple quark questions that are going to come up. My point is, there's a lot of highly theoretical things here that you don't necessarily need for your diploma exam. Like, you can't just skip this section. Like, don't do that. But you need to know that this is where physics is going, and it's kind of an introduction just to get your feet wet, kind of to the next levels of physics. So, take this with a grain of salt. You may have to read the sections of the textbook as well as going through these notes. That would certainly be helpful to increase your understanding. Anyways, let's get on with it and let's see where it goes. So part 1, detecting and measuring subatomic particles. So, how do you find a particle you can't see? Well, hunters and guides have been doing that for centuries. They've been able to discover a lot about animals just by looking at their tracks. So, in a very similar way, scientists use tracks for these subatomic particles to figure out a lot about them. So there's 2 methods scientists use to track subatomic particles. The first one is called a cloud chamber. So, this consists of a dust-free chamber of air that is supersaturated with vapor. What that means, it holds more vapor than it should. They play with the temperature, play with the pressure, okay, and they end up with more vapor, okay, and in such as water vapor or ethanol vapor, okay, so ethanol gas, okay, then should be allowed to be in the air at that time. And again, they do that with temperature and pressure. Okay, because the air is supersaturated, when a fast-moving charged particle zips through the chamber, some of the molecules ionize and then condense. This leaves a cloud track where the particles have been. Okay, so the second method is a bubble chamber. So this is the opposite of a cloud chamber in that a liquefied gas, such as xenon, hydrogen, helium, or propane, is used. Okay, the pressure in the chamber is lowered to reduce the gas's boiling point. Okay, as a charged particle speeds through this chamber, it again ionizes the liquid, causing it to boil. The result, or the tracks, are then tiny bubbles, okay, along the path taken by the particle. Okay, so then how is the charge to mass of a particle determined? Okay, we use magnetic fields, much is described about the nature of the particle. Okay, a charged particle would deflect one way in a magnetic field and the opposite way if an oppositely charged particle, right? Okay, and of course these things go straight if they're neutral. Okay, a mass can also be determined due to the radius of the deflection. The mass relates to the damage the particle can cause when bombarding tissue. So if it hits you, how much damage is it going to cause? Okay, the more massive the particle, the less it penetrates. Okay, and then the less damage it causes. See, this is counterintuitive, because if you think if a bigger thing hits you, it'll hurt more. But you guys all have skin, and that skin is really good at protecting you from these particles. So larger particles can't get past your skin. Okay? Whereas the smaller ones, they can get through your skin into the softer tissue underneath and cause more damage. So again, the more mass of the particle, the less it penetrates, so the less damage it causes. All right, so let's have a look at some of the practice problems for this. This particular section, okay, deals, like we've seen these kind of things before. Okay, so let's just have a look. Measurement of a particle track shows a radius of deflection of 8.66 times 10 to the negative 4 meters for a proton traveling at that speed. Okay, perpendicular to a 5.10 Tesla magnetic field. Calculate the charge to mass ratio for a proton. Okay, so here we talk about a radius of deflection in a magnetic field. Okay, well, we've seen this before last unit. Okay, in order for the forces to equate, we have a magnetic force that causes a centripetal force. Okay, and you'll remember the magnetic force is QVB, and the centripetal force was mv squared over r. Okay, of course, you'll remember that one of the velocities always cancels, so we end up with QB equals mv over r. Now, it's important to note at this point, and probably have before, that mv is momentum. So you will see every now and then they'll give you the particle's momentum and say, hey, go from there. Okay, you might get a little confused by that because, wait a sec, what cancels? But remember, once this v squared part, the squared part cancels, this is just momentum. Anyways, carrying on. Okay, we want the charge to mass ratio now. Okay, we can erase this because that's just a what if. Okay, so if we want the charge to mass ratio, remember that's the charge to mass. Okay, charge divided by mass. So then we just manipulate the formula. The mass has to divide down, okay, and the magnetic field has to divide out of there as well. So we get V divided by BR. Okay, so the charge to mass for this thing, so the velocity was 4.23 times 10 to the 5 meters per second. Okay, the magnetic field was 5.10 Teslas, and the radius of deflection was 8.66 times 10 to the negative 4 meters. Okay, so when you type all of that in, we end up with 9.58 times 10 to the 7 coulombs per kilogram. Okay, and please feel free to check my math. Okay, but that is what we end up getting. Awesome. Okay, next question. Determine the radius of the path of an electron moving at a speed of 3.2 times 10 to the 5th meters per second, perpendicular to a 1.2 millitesla magnetic field, right? The M, of course, means milli, so that's 10 to the negative 3. So again, as soon as you see this radius of a path, okay, that gives you the FC. Now remember, we get a centripetal force with a magnetic force and with an electric force, so they can trade those out. Okay, but in this case, it's a magnetic field, so that is a magnetic force. So that's going to be mv squared over r again, and qvb. Okay, as always, one of the v's cancels. Okay, great, and this time I'm looking for the radius. Okay, so that's going to go up, and the q and the b are going to go down. So my m V over QB is going to equal my R. Okay, now I'm just going to put the R over here because that's just easier for me. Alright, so the mass of an electron, okay, so that is 9.11 times 10 to the negative 31 kilograms. Okay, the velocity, we are told, is 3.2 times 10 to the 5 meters per second. Okay, the charge on an electron, of course, is 1.60 times 10 to the negative 19 coulombs. And the magnetic field, of course, is 1.2 milliteslas. So remember, milli is 10 to the negative 3 Teslas. Okay, so when we type all of this in now, all right, calculator out, so 9.11 times 10 to the negative 31 times 3.2 times 10 to the 5th divided by 1.60 times 10 to the negative 19, 1.2, negative 3. So remember, on your calculator, usually you put the bottom part in brackets. Okay, again, nothing you guys don't know. And the radius works out to 1.52 times 10 to the negative 3 meters. Fantastic. Okay, so again, it's not that you haven't seen this particular material before. Okay, it's just a new application of it. So that is great. So I'd like you guys to practice this material by doing section 17.1 in your textbook. It's on page 835. Okay, and I want you to do questions 1 through 6. You can use your textbook, or of course you can print out the PDF page on your workspace card. Thanks so much. See you next section.